Maybe the simplest concept for parameter estimation is the method of moments. And what this is where we have a sample and we can work out the sample moments, maybe sample mean or the sample variance. And then we know what the population mean and variance would be if I knew the parameters, and then just selecting or estimating the parameter values to match my sample moments to the population moments. So we take a simple example, and in probability, simple examples don't get much more simple than coin flips. Let's say we flip a coin 10 times. We don't know the propensity of this coin to land heads. We just know it lands heads with probability P, and P is a parameter that we don't know. Under that assumption, then, the number of heads, if we call that x is a binomial variable where number of trials n equals 10 and probability parameter P is not known. But let's say I ask 5 people to flip this coin 10 times each. The first person comes back and says they got 3 heads. The next one says they got 2 heads, then 5, then 4, then 3. Obviously, this isn't a great sample of just 5 data points, but I can still use it to estimate the unknown parameter P. And so I do that by calculating the sample moments and matching to the population moments. Now, in this case, there's only one unknown parameter, P. So there's only actually one, I only need to work with one moment. And so the expected value of x, a binomial with parameters 10 and P, the expectation of that is just 10p. But if I work out the first sample moment, because if I'm just working from the first population moment, the expectation, what's the first sample moment? What is the average of my sample? Well, I add up 3, 2, 5, 4, and 3, divide all of that by 5, and I get 17 on 5. So what I would get then is I would say, well, if my population first moment is 10p, and my sample first moment is 17 on 5, well, if 10p has to be equal to 17 on 5, then p, and I've called it p hat, subscript mm, p hat to say it's only an estimate of p. I don't know what p is, but I estimate p, and I've put subscript mm to indicate the method of moments. P hat mm is 17 on 50, or 0.34, so 34%. And that should be fairly intuitive, because in fact, that's obtained by saying, well, I got 17 heads out of 50 flips in total. So my best guess of the propensity to land heads is 17/50ths. Now that example was relatively simple. There was one parameter to estimate, P, so I only needed one moment. Although I said it's a one parameter problem, the binomial, of course, is 2 parameters. But in this scenario, I knew the coins were only flipped 10 times, so I already knew one parameter. So it was handled as a 1 parameter distribution. But of course, I could have done that where I just said, flip the coin a fixed number of times and report the number back to me. But I don't know the number of times it was flipped each time. and I may have to estimate that as well. And that would make it a two-parameter problem, estimating n and p. Let's take a different two-parameter problem. So estimating the upper and lower bounds of a uniform random variable between a and b. A is the lower bound, b is the upper bound, but I don't know what either a or b is. Well, the density function, I hope we remember, the rectangular slab of probability density, nothing below a, nothing above b, and constant height, 1 over b minus a, between the lower limit and upper limit. Well, if I work out the first two moments of that, the expectation, I can just work out that it's the middle of the rectangle, and fair enough, it is b plus a over 2, so the average of the lower bound and the upper bound. The second moment's a little bit more complicated. But what I get to is I get to this statement that depends on the lower bound and the upper bound, so b squared plus ab plus a squared all over 3. So I've now got the population, if I knew the parameters a and b, the population first and second moment. Now let's say I've got a set of observations, and the observations are 0.5, 7.1, 4.2, 3.7, 2.2. Well, I can work out the first sample moment just by adding those up. There's 5 of them, and then dividing by 5. So please feel free to check my arithmetic, but I got those adding up to 17.7. Divide that by 5, 3.54 is the average of them. Similarly, I squared them all, added up the squares, divided by 5, and I got to 17.366. So I got the first and second sample moment. So my problem now to estimate a and b is just to say which a and b will give me a population first and second moment of 3.54 and 17.366 respectively. So now I've just got a problem with 2 simultaneous equations and 2 unknown variables. Now the first one of these is quite easy to work with, because if I know that b plus a on 2 has to be 3.54, then rearranging that, I know that a has to be 7.08 minus b. Now, if I substitute that into the other statement, replacing the a's with 7.08 minus b, then I eliminate a, and I've got a statement in b, albeit one that's nonlinear. It's a quadratic equation. If I rearrange that quadratic equation, multiply both sides by 3, tidy up the terms, and what I will get to, I'll need to work out, I can do it by completing the square or by calculating the discriminant, which I hope we're all familiar with. So if I do that, my 2 solutions for b, because the quadratic equation will have 2 solutions, maybe not distinct solutions, but 2 solutions. So I'm going to get b is 7.08 plus or minus the square root of 7.08 plus 4 times 1.9716 all over 2. So now work out what those are. Solving that, I'll get 2 possible values. Now if I look at those, one of them doesn't make any sense, because one of which is smaller than my smallest observation. So if that's the upper limit, doesn't make any sense. So I really want the positive one of those. Now, if I take the positive one of those for B, I say B has to be approximately 7.3483. Then what do they have to be? Well, A has to be 7.08 minus B. So in fact, I would estimate A to be the other one of those. Now, both of those, I put a hat on to say it's only an estimate, and I put the subscript MM to say I got there by the method of moments.